Hi, so for today we're going to continue our discussion all about thermal physics, but we will be dealing now with the quantities of heat. So energy transfer that takes place solely because of temperature difference, that is a temperature difference between two bodies, is called the heat flow or the heat transfer. And energy transferred in this way is what we call the heat. And again, from our previous video, we said that heat is flows from the high temperature to low temperature. So there is an experiment created by Joule. According to Joule, the temperature rise is directly proportional to the amount of the work done. So we have here a water paddle that is being run by a certain load here. So Joule said that if this water paddle has a greater work or spins faster, then the temperature because of that work will go higher. So the water warms as the paddle does work on the water. The temperature rise is proportional to the amount of the work done. So it means that more work done on that water means more temperature rise. So it means that the amount of work done is actually proportional to the temperature rise. So we can warm up water by using this paddle by applying work in this water, but direct heating can also produce the same temperature change as doing work on the water. So as you can see, we have an application of this in our homes whenever we have to boil some water, okay? And we have observed that the greater the fire or the heat, the intensity of the heat, the shorter the time for the water for its temperature to rise. But if we have a large amount or volume of water, okay, and we apply low heat, then definitely it's really hard or it really takes time for that water's temperature to rise up. Okay? So in other words, he said that the amount of work done is proportional to the temperature rise or vice versa. So let's define some terms. So what is a calorie? Calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.15 degrees Celsius to 15.5 degrees Celsius. Or in other words, amount of heat required to raise the temperature of 1 gram of water for 1 degree Celsius. That is the calorie. This calorie is another unit for heat. Okay, so this is the English unit for heat. Now we have also what we call the British thermal unit is defined as the quantity of heat required to raise the temperature of 1 pound. That is basically 1 pound of water by 1 degree Fahrenheit. So British thermal unit is actually known as also BTU. Okay, and here are some following conversions from calories to joules. Joules is the SI unit of heat, and from BTU to calories and to joules. So we have for 1 calorie, we have 4.186 joules. You have to bear in mind this constant because it's very important that in some of the problems in physics, uh, the given parameters are in terms of calories, but the final answer may require the joules, the amount of heat in joules. So you have to have or to memorize this conversion. So 1 kilocalorie, that's equal to 1,000 calorie, and that's basically equal to 4,186 joules. For the BTU, we have 1 BTU is equal to 778 foot-pound, or that is equal to 252 calories in terms of calories, and in terms of joules, BT and in terms of calories, it's actually equal to 252 again. And in terms of joules, 1 BT is equal to 1055 joules. We have no other option but to take note of this conversion. Well, in fact, it's not really hard for now because we're only on the introductory part of the study of heat. So again, the quantity of heat in terms of formula required to increase the temperature of a mass m. Okay? For example, we have a temperature or we have an object of mass m of a certain material from T sub 1 to T sub 2 is found to be proportional to the change in temperature in the mass of the material. Or in other words, we have the famous equation wherein Q is equals to MC delta T. So what is this Q? The uppercase Q that denotes the heat required in maybe in joules, in calories, or maybe in BTU. That is equal to the mass times the C, which is the specific heat of a material, which is defined as the amount of heat required to raise the temperature by 1 degree Celsius for the mass 1 kilogram. Okay, that is basically the definition of the specific heat. 1 degree heat required to raise the temperature of a mass 1 kilogram mass by 1 degree Celsius. Okay, don't be confused with the definitions of the calorie, British thermal unit, and the specific heat. Okay, and delta T is basically the change in temperature. Okay, so it is also found out that according to this equation, the greater the mass, the greater amount of heat required for this to increase the change in temperature. Okay, it makes sense if you are going to boil a water, let's say applying an amount of heat of let's say 100 joules with a mass of water, let's say 50 grams, it's easier to boil, okay, than for a 1,000 or 10 kilograms mass of water. Okay, so it's easier to boil the 50 grams than the 10 kilograms. And of course, the mass is proportionate to the heat required. Okay, the greater the mass, the greater the heat required for that object to have a change in temperature. Okay, so here is the specific heat of water. Well, let me have a correction in this. The specific of heat of water is basically, I'm just going to write. So basically what we are using for the specific heat of water, let's have this. So that's basically denote as we have a formula Q is equals to MC delta T. Okay, wherein if we're going to define what is C, that is the specific heat, let's say the specific heat of ice, specific heat of water, and specific heat of steam. So these are the important specific heat that we should know. So for specific heat of ice, basically is we have 2090 joules per kilogram degrees Celsius. For the sea of water, we have 2. So we have 4.186. That is basically, let's say, joules per gram degree Celsius. Notice that this is in terms of grams. Or if we are going to convert it into kilograms, we have 4,186 joules per kilogram degree Celsius. And for the specific heat of steam, we have 2010 joules per kilogram degrees Celsius. Okay? So, we must be consistent again in the unit of the masses. Okay? And also, for the units of temperature, again, we have the same. So, the specific heat of water in terms of Kelvin is the same. 4.186 joules per gram Kelvin, or in terms of kilogram, that is also the same as 4,186 joules per kilogram Kelvin. That is basically the same. Okay, because the change in temperature again in Celsius is the same change in temperature of Kelvin. Okay, so these are the important specific heat that we need to know. Okay, for at least for the water. Okay, let's go back to our lecture. So we have here, so the approximate specific heat of water in terms of calories is 1 calorie per gram degree Celsius, or in BTU, that's 1 BTU per pound degree Fahrenheit. Okay, let's have some problems in terms of Q is equals to MC delta T. Okay, so let's have this problem. An 80 kilogram man has run a fever of 39 degrees Celsius instead of the normal body temperature of 37 degrees Celsius. So from there, we have the given, we have the mass of 80 kilograms. And again, the man has a fever. So basically, we can say that the final temperature of that man is 39 degrees Celsius and its initial temperature is 37 degrees Celsius. Assuming that the human body is mostly water, that tells you something, okay? How much heat is required to raise his temperature by that amount? We are required how much heat, and that is basically the Q, okay? So the C that we are going to use here is basically the C of water, or the specific heat of water, and that could be 4.186 joules per gram degree Celsius, or 4,186 joules per kilogram degree Celsius. So let's compute what is the amount of heat required to raise its temperature by that amount. That is equivalent to Q is equals to, again, M mass times the specific heat times the delta T. So we have the mass, which is 80 kilograms. Specific heat, oops, what are we going to use here? Since this is in terms of kilograms, our mass is in terms of kilograms, we have to use the value for the specific heat of water that is in terms of kilograms, 4,186 joules per kilogram degrees Celsius. So that is our specific heat, and the delta T is basically the final temperature minus the initial temperature, 39 degrees minus 37 degrees Celsius. And if you're going to compute that, we can see that the units cancel: kilogram, kilogram, Celsius, 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 and then we are left with joules. Computing that, let me just see the answer here. We should have an answer of 669.76 kilojoules. So 669.76 kilojoules, or in other words, that is equivalent to 669.76 times 10 raised to 3 joules. That should be our answer. Okay? So the specific heat of water is not given. So it is assumed that the students know what is the specific heat of the water. So number 2, we have here, how much heat must be absorbed by 375 grams of water to raise its temperature by 25 degrees Celsius. So again, we have the mass that is equivalent to 375 grams, and we are given a temperature here. So how much water, how much heat is required to absorb by the 370 grams of water to raise its temperature by 25 degrees Celsius? Now, my question is, what is this? Is this the initial temperature or the final? Okay? So, if it's going to be raised at a temperature of 25 degrees Celsius, then that must be our final temperature. Okay? And again, our problem is asking is, what is the heat? How much heat? So that's the Q. So we have here the formula again, MC delta T. So we have the mass, that is 375 grams, times the specific heat. Again, the specific heat of water in terms of grams is 4.186 joules per gram degree Celsius. So we have 4.186 joules per gram degree Celsius times delta T. Our final temperature is 25 degrees Celsius. If there are no given, we assume that if there are no given initial temperature, we assume that it is 0 degrees Celsius. As you can see, units will cancel. So, and again, if we're going to compute that using our calculator, we shall get an answer of 39.2 kilojoules. So 39.2 kilojoules. Okay, very easy, right? So number 3, what mass of water can be heated from 25 degrees to 50 degrees Celsius by the addition of 2,825 joules? So we have here given, our given is the final temperature, that is 50 degrees Celsius. Okay? The initial temperature is 25 degrees Celsius, and the heat, okay, addition of heat is 2825 joules. So we are being asked what is the mass of water that can be heated using this by the addition of this amount of heat. So using our formula, Q is equals to mc delta T. We have Q, we have to get M, we have to express M. So that would be Q over C times the delta T. So we have the Q, that is 2825 joules over the C of water. Let's use that in terms of grams. So 4.186 joules per gram degrees Celsius multiplied by the delta T, which is 50 degrees Celsius minus 25 degrees Celsius. Okay? And that should be, that the units should cancel, joules, joules, degrees Celsius. So we are left with grams as our mass. And if we're going to calculate that using our calculator, we shall get an answer of 27 grams. Well, of course, if we use the C, which has a kilogram in it, well, we expect that the result should be kilogram. Okay? So, yeah. Is it clear? Yes, it's very easy. That's an easy problem. So, let us try another one, number 4. Okay? What is the final temperature when 625 grams of water at 75 degrees loses 7.96 times 10 raised to 4 joules? Okay, so we have a great concept here. Okay, so let's write the given. M is equals to 625 grams. Okay, and our Q is actually 7.96 times 10 raised to 4 joules. And the initial temperature is given by 75 degrees Celsius. So we are asked for the final temperature. Now, if the problem says that it loses heat, okay, it loses heat. So it means that our heat should be negative. Again, if the problem says that the object loses heat, we have a negative Q. So let's write negative Q loses heat. And if it's absorb heat, in other words, then that should be a positive Q. Absorb heat or gained heat, that should be positive. Okay, so in this case, we have the formula Q is equals to, again, mc delta T. But since our problem says it loses, so it implies that our Q should be negative. So the final temperature, we are being asked for the final temperature. So what are we going to do? Negative Q over mc, and our delta T is basically T final minus T initial. Okay, so what are we going to do here is basic algebra. So we are asked to find for the final temperature, and our final temperature is basically initial temperature minus Q over M times C. So our initial temperature is 75 degrees Celsius minus the Q, that should be 7.96 times 10 raised to 4 joules, divided by the mass of 625 grams. Basically, that is still water. So it is in terms of grams. So we have to use the specific heat of water in terms of grams. 4.186 joules per gram degrees Celsius. Okay? So if we manipulate those variables and calculate it using our calculator, therefore our final temperature, we shall arrive at a final temperature that is 44 degrees Celsius. Okay? So that should be our final answer. So let me just double check. Okay. So 44 degrees Celsius or 44.5 according to our calculation, 44.5 degrees Celsius or even 45 degrees Celsius. Okay? So, let's go now to our problem number 5. So, for our problem number 5, a 65-gram piece of iron at 525 degrees Celsius is put into 635 grams of water at 15 degrees Celsius. What is the final temperature of the water and the iron after putting it together? So as you can see here, we have two entities. We have two objects, the iron and the water. So if the iron is to be put inside the water or in the water, then after some time, there should be a thermal equilibrium existing between these two objects. In other words, the temperature of both the iron and the water should be the same. Okay? So that's thermal equilibrium. So again, so we have to write the given. So we have the mass of iron, and the mass of iron is 65 grams. Okay? And the initial temperature of the iron is 525 degrees Celsius. Okay? And please forgive me, I forgot to actually include the C of iron, and that is basically equal to, if I'm not mistaken, 0.45 joules per gram degree Celsius, if I'm not mistaken. Okay, so that's the C of iron. And again, for water, we have the M of water, that is 635 grams of water. We have the C of water, and that is 4.186 joules per gram degree Celsius. And we have the initial temperature of the water, which is 15 degrees Celsius. So, we have two Q's here, okay? And the key concept is that the Q gain should be equal to the Q loss, or the heat gain should be equal to the heat loss or loss, diba? So, heat loss. So, what are we going to do is that in this case, the object that gains heat, okay, that gains heat is actually the water. Okay, because when the iron is placed inside the water, the temperature of water rises. So the water gained an amount of heat. So that is, if the water gained an amount of heat, that should have a positive sign. Okay? Or in other words, that is equal to the amount of heat, so lost, okay, lost by the Q of iron. And that should be negative because it loses heat. Okay? So again, if the object gained or absorbed heat, that should have a positive sign of Q. And if the object loses heat, that should have a negative Q. Okay, so the key concept is the heat gain is equal to the amount of heat loss. Okay, so in this case, if we're going to rearranging the equation, Q of water is now plus the Q of iron, and that should be equal to 0. Okay, so can we solve now for the final temperature? Yes, we can solve. So for the Q of water, we have M of water, the C of water times delta T, plus the M of iron, the C of iron times the delta T, and that should be equal to 0. Okay, so what is the mass of water again? The mass of water is 635 grams. And the C of water in terms of grams is 4.186 joules per gram degree Celsius. And the delta T, the final temperature we don't know, that's the unknown, minus the initial temperature of the water, which is 15 degrees Celsius, plus the mass of the iron, that is 65 grams. And the C of iron is given above 0.45 joules per gram degree Celsius. And the delta T we don't know, that's the final temperature minus the initial temperature of the iron, and that should be equal to 0. So this require a lot of algebra. So what are we going to do is if we multiply basically both of these two, 4.186, okay, 635 times 4.186, we should get a value of 2658.11. And if we're going to multiply it here, distribute this, we shall have 2658.11 T sub F minus 2658.11 times 15, and that is equivalent to 39871.65. Let me just disregard first the units. So plus, we have here 65 times 0.5. Okay, that is equivalent to 29.25. Okay, so are we not okay, the mass of iron is 65. Okay, 29.25 times it, distribute this into this. Okay, so we have TF 29.25 times 525. That should be equal to 15356.25 is equals to 0. So now we can solve for the TF, and the TF is basically combining like terms. We have 2658.11 TF plus 29.25 TF. So 2658.11 TF plus 29.25. So we have 2686 T sub F. And if we're going to place these two negatives constant on the other side of the equation, we shall have 39871.65 plus 15356.25. Okay, and if we're going to solve for F, so we have now the 39871.65 plus 15356.25 divided by 2687.36, and the value of our T sub F should be what? 20.6. So 20.6 degrees Celsius, which is actually really correct. Why? Because the temperature of the final temperature of the both substance should not be greater than 525 nor less than 15 degrees Celsius. It must be in between, which is actually correct. 20.6 degrees Celsius. So going back on our PowerPoint presentation, let's proceed. So there's what we call the latent heat of fusion and vaporization. Basically, this involves the phase change. For example, how much heat is required to uh, raise the block of ice of water into vapor. So basically, that could happen, and it requires a large amount of heat in order for that ice to become first water, and then from water it became steam. Okay, and basically that is where the latent heat of fusion and latent heat of vaporization enters. So the concept of that. So the latent heat of fusion is basically the amount of energy required to convert a unit mass m of a solid, for example, an ice, into a liquid without a change in temperature. So basically, when the object changes its phase from solid to liquid, the amount of heat required to change that phase from solid to liquid is what we call the latent or the latent heat of fusion. It has the following formulas, which is equal to Q is equals to the mass times the latent heat of fusion. Latent heat of fusion for different materials, okay, occur in various numbers. For example, for water, for iron, for everything, it has a specific latent heat of fusion, and that is basically from solid to liquid again. And we also have what we call the latent heat of vaporization. It's basically the amount of heat energy required to convert mass m of a liquid into vapor without a change in temperature. One example is that if you're going to boil a water, you can see here that when the liquid or the water starts to boil, it is being converted into vapor. And how much energy is required? And that is basically given by this formula. Q is equals to mLV, where LV is the latent heat of vaporization of that liquid material. So in order for us to fully understand the phase change, so we have here a table. This is the heat in terms of x-axis, and this is the temperature in terms of the y-axis. So for example, we have an ice that is in no heat added. So as we increase the temperature for 0 degrees Celsius, it starts to melt. Of course, water starts to melt at 0 degrees Celsius. And as we increase the heat added for this melting process, we can see here that there is no change in temperature when the melting process is being done, or from solid to liquid, there is no change in temperature. And if we're going to increase again the temperature, it now became water. Why? Once it melts, it became water, and when we increase the heat added, okay, we are actually increasing also the temperature. We increase the heat, okay, and until we have reached 100 degrees Celsius, basically that's the boiling point of water. The water now will start to become vapor. And as you can see here, we have a linear straight line here purely on the x-axis, because during the vaporization stage the water does not have a change in temperature because there is a change in phase. That's very important, the concept of thermal physics. Once the object undergoes a phase change, there is no change in temperature. Okay? So here are some heats of fusion, okay, and vaporization of some material. We just have to take note of the latent heat of fusion of the water, which is basically what? This 334. So the latent heat of fusion of water is 334. Okay, 334 times 10 raised to 3 joules per kilogram. And the latent heat of vaporization of water is actually what? 2256 times 10 raised to 3. Okay? So joules per kilogram. That's very important. And some of these values, hydrogen, oxygen, constants for latent heat of vaporization and fusion, are always given. Okay? Except for, well, of course, for water, because it is assumed by the someone who gives us exam that we know that constant. Okay? So, but if it is given, it's much better. Okay? So, for our last problem, I've copy pasted that in our notepad or journal pad. So, here, calculate the total energy needed for a 100-gram piece of ice at a temperature negative 40 degrees Celsius to convert it into steam. Okay? You can see here, from ice to steam. So definitely there is a phase change. From ice to water, then from water to what? To steam. Okay? So there is a phase change here. Definitely we'll be using the latent heat or the latent heat of vaporization and the latent heat of fusion. Okay? From negative 40 degrees Celsius to convert it into steam of 110 degrees Celsius. So, the total charge, the total heat, I'm so sorry, I confused Q with the charge. The total heat required is actually equal to what? The mass of ice, the C of ice, because it is still in the ice, negative 40 degrees Celsius, the ice is still at ice. So, delta T. Okay? So, M of ice, C of ice, times delta T. Once it reaches 0 degrees, okay, the ice starts to melt. And that is a phase change. So, we have to include the M, L, F. The mass of ice or the water is still the same, 100 grams, multiplied by the latent heat of what? fusion. And latent heat of fusion is basically from solid or ice to water. That's the amount of heat required to convert that piece of solid into water or to liquid. So that's what MLF. Well, of course, we have to add. So after this computation, it became water. So we have the mass of water, the C of water. So we have to add another heat for that 0 degrees Celsius of ice that starts to melt into water. We have to increase its temperature up to 100 degrees. So we have here again the delta T. And once the water reaches 100 degrees Celsius, it starts to become steam. So there is a phase change from water again to from liquid to gas. So we have to add the mass times the latent heat of vaporization. Okay, there's a phase change. There's no change in temperature during the phase change. But we're not yet done because the temperature we have here, delta T, is 100 degrees Celsius. Okay? But we are asked up to 110 degrees Celsius. So what are we going to? Is what? The M of the steam, okay, times the C of the steam times delta T. Okay, that's the total energy needed for a 100-gram piece of ice at negative 40 degrees Celsius to convert it into steam of 110 degrees Celsius. So what are we going to? Let me just first convert the 100 gram into kilogram because what we are going to use for LF and LV is in terms of kilogram. So we have 100 grams is 0.1 kilogram. And basically the C of ice, we have that a while ago. The specific heat of ice is 2090 joules per kilogram degrees Celsius. And delta T is actually from our final temperature is for that to reach it to 0 degrees. Okay? Because this is the melting point of ice. So 0 minus negative 40. Take note that the initial temperature is negative 40 degrees Celsius. So we have to include the negative, and we have a negative sign here. This becomes positive. Plus, we have the mass during the latent heat of fusion. That is still 0.1 kilograms. Okay? So, the latent heat of fusion, again, for the water is basically equal to 334 times 10 raised to 3 joules per kilogram. Okay? So, we are done with MLF. Once the MLF has been done, okay, the object became water. So the mass of water is still the same, 0.1 kilogram. And the C of water in terms of kilogram is 4,186 joules per kilogram degrees Celsius. And delta T, of course, from 0 degrees up to 100 degrees. So our final temperature is 100 degrees Celsius because this is the temperature that the water starts to boil. Minus our initial temperature. Again, we don't have any change in temperature in latent heat of fusion stage. So our initial temperature will be the final temperature for the ice. So 0 degrees Celsius. Okay? Plus, once it reaches 100 degrees Celsius, the water starts to become vapor or steam. So we have to include the MLV. So that is still 0.1 kilogram times the latent heat of vaporization of the water, 2256 times 10 raised to 3 joules per kilogram. Okay? And lastly, so when it became steam, okay, we must add the mass of the steam. That is still 0.1 kilogram. Okay, let me just rewrite this. So that is 0.1 kilogram multiplied by the C of steam, the specific heat of steam, that is 2010 joule per kilogram degrees Celsius times delta T. Our final temperature is 110 degrees Celsius finally minus 100 degrees Celsius. And if you're going to calculate it, very long calculation, but still worth it if you're going to get the correct answer. So we have followed the same concept. So what are we going to get is, according to our final answer, that is 3.12, 3.12 times 10 raised to 5, oops, times 10 raised to 5, okay, joules. So basically, this is the amount of heat required for that ice to be converted into steam of 110 degrees Celsius. And of course, for your, well, additional work, if you wish to, you can stop this video and copy this for your additional problem. And let me just uh, give you some hints in this. So this will be your practice problem. Well, of course, for you to be able to uh, still practice the calculation for heat. Here are some problems. So again, thank you so much for listening and God bless you. And I hope you learned a lot in this video. Thank you.